Hi there. In this video, I want to show you how to create a parcellation algorithm, which is based on the grid structure in Grasshopper. So let me maybe show what I want to get in the end. Maybe not this, but something like that. So for this algorithm, we will already start with some city blocks, like these regions here. And what I want to get from this algorithm is this subdivision. So it should be able to just divide the city blocks into smaller city blocks or parcels. No, not a big difference between them actually, according to the width and depth numbers which I have here. So I should be able to control sizes of the individual cells. So this algorithm is pretty useful because sometimes if you work with some geometry which is given by user, like this boundary and streets, which the user also draws, sometimes means that the size of elements will not be homogeneous. And sometimes, like in this case I want to show now, you will see that some city blocks are really small, like these two at the top, and some city blocks will be really huge. It just can happen like this, right? So if the user draws the streets like this and the boundary like this is what you get. And sometimes you really want to unify it somehow and to break it into pieces which will all approximately have the same area and the same dimensions, so that you can apply some further scripts to them. So in this case, this parcellation script is actually not used to generate parcels, but it is used to generate secondary street network here. And later on, basically the same script is used to generate parcels inside these city blocks. And you see how homogeneous it looks like. And it basically makes it very easy to operate on this geometry. And also just let me show how it will behave if I extend my streets so that they actually cut the boundary. This is what happens, right? So I also want this script to find the prevailing direction of each city block and to break it down into smaller city blocks based on this prevailing direction. So you see that the grids are aligned differently in each of the city blocks. So let me maybe start with creating the script. I will basically start from scratch so that you can follow what I'm doing here. And later on, I will publish other videos on further topics. And so we will, based on these videos, we will create more and more complex scripts. Okay, so I'm starting with this file, which only has the small group here inside. So what I did here is I referenced my boundary to the boundary input. This is just a regular curve data component. And second data component is called drawn streets. So I just selected the streets and referenced those to the drawn streets. Then I'm using the surface split component to split this larger boundary into smaller city blocks. And then I apply the built-in offset curve with the offset value of -4 or -5 meters, whatever you want, to create the city blocks. So this is where I'm going to start building my parcellation script from. Okay, so important is that we work with multiple inputs at the same time. This will basically allow us to think about the data structure and about how to work with lists and data trees right from the beginning. Because sometimes you probably already know that if you create your script around only one object, sometimes when you try to scale it and you try to apply it to 3 or 5 or 10,000 objects at the same time, it sometimes simply breaks because you did not manage all your data streams correctly. And sometimes you apply graft, sometimes you apply flatten to change the data tree structure, and sometimes it just breaks everything down. Yeah, of course, it is also a proper way to start with one object and then try to go through this file and readjust it so that it also works with multiple objects. But this script is quite simple, I would say. So I will start with multiple inputs at the same time. The script is based on the bounding box of all my street blocks. So let us create the bounding boxes. Basically, yeah, you see that the bounding box component already created some bounding boxes over my city blocks, which is nice. They are still not oriented correctly. You can see that all of them have vertical and horizontal edges, but this is fine for now. I will come to it a bit later and show you how to make these bounding boxes actually align with your geometry. As the next step, I want to split those boxes or rectangles into cells, into rows and columns. One way how you can do it is to use domains. So if you go in the math, domains, you will see this component called divide two-dimensional domain. I'm going to use this component. So it takes the domain itself, uCount, and vCount. So in this particular context, u and v directions is basically the same as x and y directions. So you can just perceive them as x and y. It doesn't matter that much. So based on this image, you can see what it does. It takes some domain. Like a normal domain is just a range of numbers from value A to value B, right? So you have this construct domain here. You can construct domain from 7 to 15.7. And the result will be just 7 to 15.7, right? So it's just a range of numbers. Two-dimensional domain is basically the same thing, but instead of having only one pair of numbers, you can have two pairs of numbers. So you can think of it as like a range of some numbers in x and the range of some numbers in y directions. I hope you'll understand it a bit better when we start actually working with these domains. So let me start to do it. I want now to calculate domain, which will basically just mean size of my bounding boxes in meters. I want to calculate it for my bounding boxes. So I want to have the two-dimensional domain, which will have x value of width of this rectangle and y dimension of height of this bounding box. So to get dimensions, I can use the dimension component, get the approximate dimensions of a surface. I connect my bounding box to it, and in the outputs you will see sizes of these domains in meters. So u or x for this, how many bounding boxes do I have? 5. So for these 5 rectangles, I have x sizes of 750 meters, 1150 meters, 525, and so on. And the same for v. It's just a list of numbers. Now I want to construct two-dimensional domain, which will have u and v of the first rectangle, another one which will have u and v value of the second rectangle, and so on. You can again open this domain category or subcategory in the Maps tab, and you will see construct domain to the power of 2. So it means construct two-dimensional domain from 4 numbers, and you will see the component with exactly the same name, but with a different icon. And why don't I see the description? Okay, let me create it. Create a two-dimensional domain from 2 simple domains. And as you can see, the names of inputs are exactly the same as names of dimensions. So this is something we will prefer to use here. The first one, construct a two-dimensional domain from 4 numbers, acts the same way. So if in this one you have u0 and u1, and u0 is equal to 0, and u1 is equal to 1, basically it means that this two-dimensional domain will stretch from 0 meters to 1 meters in u dimension, and it will stretch from 0 meters to 1 meters in v direction. So that's what you can see in the output. The same thing happens here, but this single u input takes any numbers or domains already. So you don't have to specify 2 numbers. You can just specify domain or just 1 number there. It doesn't matter that much. You don't actually also need to understand that good what happens inside these domains, since that's just, you'll just need domains here. After these 2 or 3 components, you can completely forget about them, and it's fine. So I want to construct my domains from dimensions of my bounding boxes. Now for each bounding box, I have this domain. Goes from 0 to 750 square meters in U or X. It goes from 0 to 527.8 meters in V or Y dimension. And the same in the same way, we have two-dimensional domain for the second bounding box, third bounding box, and so on. So these are my domains. I can now connect them to the divide domain component. Now, 2 other inputs here are U and V. But here you can see they are not specified in meters, but instead you should provide the number of segments in U direction here. So it's not some value in meters, instead that's a number of cells you want to generate. So it's 10 cells or 10 segments in U direction and 10 segments in V direction. And according to this image, this is what we want to get, right? So we want to take our domain or surface and just split it, like slice it in some columns and rows, and have this subdomains. So this is also what happens. If you check the outputs, these are our subdomains. And again, divide domain only works with numbers. It doesn't actually divide the geometry itself. So as you remember, these were our bounding boxes, but after we applied dimensions, we converted these bounding boxes to numbers, U and V dimension of each bounding box. And now we only work with numbers. So we construct domain out of these numbers, and then we divide this two-dimensional domain into multiple parts. So it means that if the first domain had U going from 0 to 749, it means that this domain, after division in 10 segments by U axis and also 10 segments by V axis, will result in 100 smaller domains, right? So, and this is what you get in the output. So you get 100 smaller domains for each branch. And you can see that U goes from 0 to 700 to 74.9, and V goes from 0 to 52.7, and then 52.7 to 105.5, and then from 105.5 to 158.3, and so on. So this just describes the first row of these subdomains. And then as the second row starts, it starts from 74.9, so exactly the same number where the previous column ended, and it goes to 149.8. So these are just numerical representations of the small slices, small cells inside the bounding box. Now to come back to geometry and to somehow apply those small slices, we need this component which is called isotrim. Isotrim. Extract an isoparametric subset of a surface. I think I wouldn't understand from this description what it does. So it just helps me that I know already what it does, and let me show it to you. Now it takes a surface and the domain. And according to this image, this is what it does. It just takes part of surface, which is described by the domain, by the subdomain here. And this is what I want also to do. So I want to connect my bounding box, which is also a surface because it is a flat box, to the surface input, and I want to connect my domains to the D input. Now, please carefully investigate your inputs, because you see that divide domain to the power of 2 gives you a data tree. You can guess it based on the type of this wire, which you see here. And by the way, if you do not see these nice wires in Grasshopper, you might need to go to Display and select Draw Fancy Wires. Otherwise, all wires will look the same. So please enable Draw Fancy Wires. And this is how you can check the data structure inside your wires. So please be careful, because isotrim currently takes 5 elements in one list in the surface input, and it takes the full data tree in the D input. So it means that I want to graft the first input so that it will also get the according according data tree structure here, containing 5 branches. So let me now check the outputs of isotrim, and you can see that they look pretty nice. So you can see that all my city blocks are now split and divided in these cells. Of course, now it is not trimmed to the city blocks themselves, so I only work with bounding boxes. I did not do anything with the original city blocks, but I can do it right now. And yeah, one more thing about it is that all my city blocks are divided in the same number of cells. So no matter what size of the city block is, this will be divided 10 by 10. We can also work with it a bit later and adjust it. Now I want to trim the cells I have here to my original city blocks. I can do it using one of the Boolean operations, and I think region intersection should help me here. So I enter region intersection, and yeah, let's try to connect something to it. So it takes A input and B input, which should be closed curves. So I enter my city block. I connect my city blocks to the A input, and result of isotrim to the B input. And again, carefully check that your inputs have the same structure. So since my isotrim result in 5 branches, each of them having 100 elements, means that my A input also should have 5 branches. Because, well, we currently have 100 cells for each city block there. So I need to graft this first input, and I don't see any results here. Well, sometimes region intersection, as other Boolean operators in Grasshopper, can be pretty buggy and tricky to set up. So if you see that it doesn't work correctly, one way to make it work would be to use XY plane and to connect it to the P input. But in this case, it also didn't happen. It also didn't help. So I remove XY plane, and let me try another way of fixing it. Let me try to change A and B inputs. So I connect isotrim to the A input, and I connect my city blocks, which I can also reference here, to the B input. And again, don't forget to graft the city blocks correctly. And this is the result. So you see now it works. I hope it also works on your machines. I'm not quite sure why region intersection failed the first time, but this is the bug I see pretty often, that sometimes you do need to change inputs here, swap them, and then it starts to work. Okay, so it looks nice. Now I need to adjust the size of my cells somehow. For that, we can go back to the divide two-dimensional domain component and check its inputs. So U and V are set to 10 here. And let me just try to enter some other numbers here and check what happens. So if I change U count here using the slider, you can see how the number of divisions in X dimension change. And the same with V. So this is the place where I can control the size of my cells, or not the size, but actually the number of cells which my bounding boxes will be divided into. Instead of a slider, I of course want to parameterize it. I want these values to be somehow dependent on the sizes of my bounding boxes. Let me introduce two new numbers, and these numbers will be the sizes of the desired dimensions of my parcels or smaller city blocks. I will enter something like 150 and 100. I can readjust these numbers later. And so these are the wished dimensions of my output cells. So I want each of the cell to be 150 in X dimension and 100 meters in Y dimension. Now, how do I apply these numbers? How do I connect it to my script? We know that divide two-dimensional domain receives these two inputs, U and V. But here we should specify number of divisions, number of segments. But I also have U and V dimensions in meters of my bounding boxes. So I know that bounding box number 1 or 0, if you count from 0, has the size of 750 meters by 527 meters. To find out how many segments I should divide it into, so how many segments of size 150 will fit there, I basically just need to divide this dimension with this number, by this number, right? So if I divide 750 by 150, I will get something roughly like 5, I guess. So roughly 5 cells would fit inside this bounding box in the X dimension. And this is exactly what I need to pass into divide two-dimensional domain here. So let me apply this division operation. I'm dividing the overall X dimension by 150. I get some number like 4.99, and I can now connect it to the U input. But of course, U count and V count can only receive integers, so they can only receive whole numbers. 4.99 is not a whole number, so I need to convert it to 1. I need to round it up. The round component will help us in this place, and it has 3 different outputs. You can choose one of them which fits your needs. I will choose the nearest. So the nearest will just pick the nearest integer to the original number. So 4.99 will be converted to 5. 7.7 will be converted to 8, since 8 is closer to 7.7 than 7. 3.49 will be converted to 3, and so on. So I'm taking this nearest number and connecting it to the U input. Let's do the same for the V, for the second dimension. So I copy the division and round components, connect V output of dimensions to the division component, and replace 150 by 100 here. Now I will also connect. I will also use the nearest output and connect it to the V input of divide domain. And now if you go to the outputs, you can see that it looks pretty nice. So my cells have roughly the same size. And even if I move my street somewhere, which will, of course, change the size of individual city blocks, thanks to these components, my division will readjust so that the size of parcels will remain pretty stable for and pretty homogeneous for all city blocks here. So this works pretty fine, and I can also generate this parcels output here. Now the only thing I might want to change is to align my bounding boxes to the original city blocks, because currently, as you remember, they're all not aligned, so they're just aligned vertically and horizontally. There is a super simple way to do it, actually. As a rule of thumb, if you take the longest edge of the curve, so for this city block here, the longest edge would probably be this one. So if you just take this longest edge and align the bounding box according to this edge, this will be the most optimal shape to generate the rectangular grid for this city block. And the same applies for all other city blocks, of course. So we just need to find the longest edge and somehow use it to generate bounding boxes. And bounding box has the second input, which will be using for it, which is called plane. It currently has the world XY plane, which is also correct, but we just need to align this plane according to our longest edges now. So how do we find these longest edges? That's quite simple. We will use the explode component, which takes any polyline and explodes it into all of its edges. So the segments output will provide us with all segments. And now I can sort these segments by their length. To do this, I first need to get the length of segments. I need to sort those lengths using the sort list component. And since I don't need the length themselves, I cannot just use this key output of sort list because I also need to sort my segments according to their length. And then I need to find the longest segment. To do this, you can use the second input of sort list, which is called A. And you can read in its description that it's optional list of values to sort synchronously. Basically means that while sort list will sort length of segments, it will also sort some data, like segments themselves, in the same way. And the A output will already contain the sorted list of segments, right? But this whole list will be sorted based on the length of the segments. Now let me take the list item component, which will help us to get the first element of this list. As you can see, we now get the smallest segments of these city blocks, simply because sort list sorts from smallest to largest, to biggest. So to get the longest item, I need to either take the last element from this list, or I can simply reverse the list before I apply a list item and thus take the last element of the original list or the first element of reversed list. So to do this, you can right-click on this L input of list item and select reverse, which I already did. And now you can see I get the list of all longest edges of my city blocks, and I can connect them to the bounding box second input. And again, please be careful with your data tree structure, because in this case, the output will be structured as the data tree, as a tree structure. So it will have 5 branches, but my bounding box already receives 5 curves without any structure, without any branches at the first place. So I also want to pass those 5 edges in the same data tree structure. I don't want to introduce any complexities here for Grasshopper. So I need to flatten inputs here, flatten outputs of list item. And now I can simply use these longest edges and connect them to the P input. Grasshopper will automatically convert those edges to planes for me. And let me check what happens now. So if I click on the bounding box, you can see that, well, we did get some results, but all of the, I guess what happens there is all of these curves got their bounding box for all of these orientational planes now, and this is not what we wanted to get. So my idea of flattening this second input did not help, because I guess bounding box will always, it will always try to generate some outputs for all different combinations of inputs from C input and from P input. So let me try to isolate them from each other by grafting both inputs. So I'm grafting the my city blocks here, and also I'm grafting my edges. So now we have a neat structure of 5 branches for city blocks and the same structure of 5 branches for longest edges. And actually, I don't need to flatten and then graft. I can just disable flatten and disable graft, because we already have the same structure here, right? And now you can see how my bounding boxes are rearranged. And for me, it looks very nice. So let me check what happens in the very last parts of my script. And indeed, my parcels look very good to me. So if I readjust any streets, I should see how my parcels readjust as well. And I'm really happy with the result. So I think I will just leave it like this and stop on this moment, because I really think this is a very good result for our intermediate step. In later videos, I will also show how to parameterize this parcel creation a bit more, how to make it more suitable for creating parcels, and how to create parcels with different size based on the distance to some attractor points or curves or whatever you select. But for now, I would say that this part of the script is already finished. Let me just create a group for it. Something like this. Okay, parcellation is finished, and I hope to see you all in further videos.